Okay, we continue. Next is Aintzane Lujambio from Arte Technology in Sevilla.
Thank you very much, Ignacio, for inviting me to this presentation and to this workshop. My name is Aintzane Lujambio, and as he said, I'm working for ALTER Technology in Seville myself. You probably know my colleagues working here in Madrid, which participate and collaborate with many of you, and with Ignacio in this Cátedra and in the different activities that are organized. But myself, I work in Seville, and I work in the microwave laboratory. So that's why I will change a bit the perspective, and I will talk more about the applications that we work for, which is basically a space, or in more general in reliability aspects. So that's the talk of my name. So it's microwave in space, and now also microwave photonics. So I too.
Or really something that is, yeah. I don't know why.
It's not moving the
slides.
No.
No.
Yeah. Thank you. So as I said, the first thing I would like to focus on is on the space. We are familiar with the space. We are hearing the news every now and then. Recently, with the Artemis launch, we have seen a lot of news about space launch, missions to the moon, and so on. And I wanted to point out a few milestones of the space sectors. And I would say that one of the most important, or the most known one, is the first mission to the moon, or the tripulated mission to the moon, which was done in the Apollo space vehicle. A small step for the man and a big one for the humanity, right? But it's not the only example. We have many other examples in the space. Another one is the International Space Station. For me, it's an amazing technology advantage. So we have been able to build and assemble a whole station in orbit. So we have manufactured each models, and we have put them into an orbit. And we have astronauts there doing experiments in microgravity. So it's a huge engineering task that we have been able to develop in collaboration between different space agencies, from NASA, ESA, and JAXA, and many others. And recently, we are seeing many other news. So I have gathered a few images that amaze me, at least. I find really impressive being able to get this type of pictures, or this launch of the Dragon demo flight, what was streamed online for anyone that wanted to see it. And why I mention all of this, it's basically because the information that we get, all the streaming, all the images, all the results of the research done, it's basically transmitted to Earth through microwave communication links. So that's why I find pretty much amazing all the stuff that we are doing in space. And this is not only the case of these examples, but there are many other examples of microwaves in space where we find different systems. One thing that also Guillermo included here, we all think, okay, microwaves, let's say, what are microwaves? I did the same. So I'm predictable, I would say, but it's not so easy sometimes to define what's the frequency range for microwaves, because if you check the literature, you find that microwaves are the range going from 3 to 30 gigahertz. Other literature says from 1 to 100, and others says from 300 megahertz up to 300 gigahertz. Well, it's not a common understanding, or not a fixed standard on this, I would say, but common thing is, as Guillermo said, that we are dealing with waves, and we are dealing mainly with waves that are comparable with the dimension of our devices. So I would say that's basically microwaves, and this is the problems that we are encountering in this field. And in this sense, these waves, electromagnetic waves, basically of these ranges, can be used in different instruments on board of a satellite. So we can find radiometers, altimeters, other observation instruments on board of the satellites. They are used also for telemetry and telecommand of the satellites, so we can really get information out of the satellite, how it's going on, if there's any issue or not, even actuate on it to change orbits and things like that. All these systems are going through communication links based on microwaves. And of course, communication systems. So we know satellite TV or things like that are also based in this type of microwave links. So few examples, more concrete ones. There are many Earth observation satellites out there. We are very familiar probably with Metasat. We all see the images from Metasat. Those satellites include many different instruments, not only microwave instruments, also infrared visible. This is the case for the Metasat, for example. We see infrared images or visible images to get information of the weather. But microwave instruments are also included in these Earth observation satellites. And I wanted to highlight one. There are many others, but one instrument that will be launched in the METOP second generation in the coming years is a microwave imaging. So it's an instrument that covers a really, really huge bandwidth. So covering from 18 gigahertz to 183 gigahertz. So it's not working in the full band, but instead it's working in small bands within the whole one, and basically selecting the peak, the different frequencies where we found the absorption peaks for different elements. And this allows the scientists to extract information about the water quantity in the clouds or the surface winds of the sea, or even the sea level, parameters like that, which may not be as accurate as a laser radar, but it's enough to get information of the whole world. So this is one very important application of microwave in there. There's another one that we are very familiar. We all have in our phones, GPS receivers. So GPS service or navigation services are basically provided by satellites and satellite constellations, in fact. So there are different, originally we call it GPS because it was the first launch by the US. It's the GPS Global Position System, but there are equivalents from different nations like GLONASS from Russia or Galileo, which is the European navigation satellite. So basically, the satellites are orbiting around the Earth, and we get a signal from there, from each of the satellites, and we can calculate our position by triangulation. So the signals that those satellites are streaming to Earth all the time are basically operated in L band, which is a band from 1 to 2 gigahertz. So we all have GPS receivers in here, and we are using microwaves to locate ourselves in the streets. So this is also a different application of microwaves in space and even for air services. And the most important one, of course, is our communication satellites. So they offer basically different communication services like TV broadcasting or internet access and satellite telephony too. And classical communication satellites are typically GEO satellites. So they are geostationary. They are in a fixed position relative to Earth, and they maintain this position and orbit together with the Earth. So we get coverage of our region, let's say Europe or Asia or wherever, by one satellite. So they are typically big satellites, over 1 ton of instrument, and they can provide very high throughput communication. So they can provide a very high capacity. And in fact, recently a new high capacity satellite has been launched, which is the ALTER-ETSIT. It was launched in September, I believe. So this is one of that. But there is another approach that has become more common and more mainstream, or I don't know how to call it, but they are LEO constellations. So it's another a different approach. Instead of keeping a satellite covering a whole area, we have a big constellation of many satellites. So this is, for example, an image taken for a launch of the Starlink. So these are a bunch of satellites that has been launched all together into a single rocket, and they have been deployed around the Earth with a much lower orbit. They need to go much faster, so they don't cover all the time the same region, but there is always coverage from one satellite or another in a specific area. So this is how we can get very good internet access. They have also an advantage compared to geosatellite, and it's the latency of the signal, because geosatellites are very close to Earth. So the traveling of the signal is much shorter in time than it is in geosatellites, that the traveling is much longer, because it's 37 kilometers orbit or something like that, 37,000. So they have benefits and advantages, each of them. And they are, at the moment, they are both approaches running together, and we can observe solutions of both approaches. In any case, they actually, the state of the art for these communication systems are based in microwave communication links. Initially, they started with lower frequencies and further increasing, and currently all of them, or most of them, I would say, are working in Ka band, so around 30-40 gigahertz, where we can get higher throughput, we get a smaller antenna size, but we are most susceptible to attenuation losses over the air, and of course also to rain fade if this happens. So it has advantages and disadvantages, and currently the technology that allows to communicate is right now there. So in any case, it doesn't matter which application it is. It doesn't matter if it was back in the 60s or nowadays. Failure is not an option in a satellite. So we need reliability of the systems. So this needs to be taken into consideration during the design of the satellite, of course. So you need to make sure how do you design your system. If you need redundancy, if you not, of course, you will for sure need redundancy, because basically you are putting something into the space, and you are not being able to fix it if something fails. So you need backup options to reconfigure the satellite to still keep it alive, or at least with a lower performance, things like that. Okay, so this is something that you need to consider during the design of the systems in all this bunch of systems, and also at component level. So basically those systems are based in small components, and most of them are electronic components, microwave components, photonic components, but they are small components that need to be reliable. Okay, so this is basically high reliability components what's in a satellite. Not only in a satellite, so I'm talking about the space because it's the sector where we work more, but it's something also to consider in many other markets, of course, in a train or in a plane or even in automotive sector. It's a different problem because you can't fix them, but of course you cannot, you need to make sure that this woman inside the car is safe. So it's also a high reliable, a market that requires high reliability in the components. But yeah, especially in space, you have the problem that you cannot fix it. So still, it's not, I would say it's more important even for space applications. So when this is basically electronics reliability concept. So what it means. So basically, we need to make sure that a device, component, a transistor, an amplifier, whatever, it performs as specified. So you design according to a given specification, and you need to make sure that it meets these specifications under some hard environmental conditions, typically, and over a period of time. So it's not, you need to make sure that electrically it performs as expected, also visually, mechanically, or optically too in optical devices. So in a space, of course, the environment is not, it's not very easy to handle, let's say. So it's very harsh. And I will discuss later on more in detail, but few factors that affect the environment conditions. I'm sure we can cover many other risks, but of course we will be having mechanical stress. We will be having a strength temperature changes on these devices. We need some endurance of these devices, and we will handle also cosmic radiation. So we are out of the microsphere of the Earth. We will suffer also these radiation effects. So having all this in mind, this is what we do in ALTER in general. I'm talking from the microwave lab. This is what I described, but it's what my colleagues do. I'm sure that you are pretty familiar with the work done by my colleagues on optoelectronics. And in Seville, we do the same with microwave devices. So we basically perform reliability testing. So we make sure that the devices that we deliver to our customers will meet those specifications for the given conditions. And we do that for a bunch of different components. So it doesn't matter an amplifier, so our active devices, passive devices, switches, oscillators, whatever it is. So just to name a few missions, we have been working commercial missions that I cannot disclose basically, but one scientific mission that I really like, I would say, because we have been working pretty hard on that. It's JUICE. I haven't heard much on the news yet about it, but JUICE is a scientific mission of the European Space Agency. It's planned to be launched next year, but it has a very exciting journey ahead because it will travel to Jupiter and it will explore different icy moons of Jupiter, like Ganymede or Callisto. But the funny thing is that it will take the satellite 7 years to reach to Jupiter. So everything needs to be assembled, tested, launched, and after 7 years, everything needs to work again and do the mission actually. So it's an example how reliability is important for space. So having all this in mind, that we need to microwave devices, we need microwave devices for communications instruments and many other applications, specifically focusing on space on communications. They are the basis of all the interchanging of data between satellites and Earth. And we are seeing that we still need more and more capacity to communicate. So I find pretty impressive to being able to stream the launch of Dragon mission, for example, through online directly. This requires a huge amount of data being shared to Earth, but still we need more. Okay, so we need higher throughput, and of course, a very important thing is keeping the same size, weight, and power levels, so that the mission is feasible. Every mass or weight that you put into the satellite is a bit more expensive to be launched. So we need to keep those parameters low. So this is the goal of any satellite communication system. And well, predictions say that, and this is present actually. So this is the transition. So communications starting with lower frequencies like S-band. Then they went to X-band because, of course, we go to higher frequencies, higher bandwidth, higher capacity, and change afterwards to Ka-band. But now there is also more things coming, and these new things coming are optical communications for inter-satellite communication, intra-satellite communication, and also from ground to Earth. And this is where microwave photonics and photonic integrated circuits will play a role. But of course, they need to be reliable, and this is the goal for these new technologies and the impressive technologies that we have, that Guillermo, for example, showed in the previous presentations. They are working on Earth, but there is a big step to put them into orbit. So this is the challenge for microwave photonics, and that's the next thing that I would like to talk is how this is done, basically. And for that, we have an example in ALTER, which is the SIFO-DIAS project. And well, I will briefly explain which is the aim of this project. It's an European research program. It's funded by the H2020 fundings, and the goal is to develop a space-grade optoelectronic interfaces for photonic, both digital and analog, very high throughput satellite payloads. So the goal can be divided in, I'd say, 3 different objectives. First of all is the digital space photonics. So one of the targets of this project is developing a space-grade optical transceiver. Second part is the one that I will be telling in or explaining in more detail is the microwave space photonics. So Jose Camani before talked about electro-optical, optoelectrical conversion. And the goal of this microwave space photonics is basically developing very high bandwidth electro-optical modulators and optoelectrical photodetectors. So this is another goal of the project. And finally, of course, this is focused into a space application. So we want to test them at module level and also at system level until reaching a TRL7 level. So TRL levels are technology readiness levels. So from the beginning, where you observe a technology, a new device performance, until it can be flown into a satellite, there are many different readiness levels. So getting to TRL7 would be proving that that technology can perform as expected under representative environmental conditions, that is into conditions that are similar to that found into space. And from that, we can find the TRL 7, 8, and 9. And 9 would mean that this technology has already flown into a satellite. Okay, so there are many, many steps to cover from the technology development up to a fully qualified device and that can be or can fly into a satellite. So in the sense, this is basically a brief schematic of one of the partners. This project, of course, is a very big project with many different partners in collaboration. We are part of it, but we are partnering, for example, with Thales Alenia Space in France, where they develop basically their own structure or a schematic of a satellite system. And I will focus in this upper part, which corresponds to the analog part of the payload, which is more related with the microwave space photonics that we will be talking later. So this basically this is a photonic. It's a repeater. So basically, it's taking signals from Earth. This is RF signal. So you have the antenna, you have the initial amplifiers, and then you are directly converting this to photonics. And then you have the core where you can process these signals. Basically, it's an interconnect in this case, in this schema. So where you can connect, for example, let's say you have one end user in this side and another user somewhere else in the Earth, and you are putting them together or connecting them together through the switch. So you connect one end with another one. So for that, of course, you need again to go back from the optical domain to the electrical domain, amplify the signal, filter it, and transmit it again to Earth. So this is a complete communication link from Earth through a repeater satellite to Earth again. So here, main building blocks are this electro-optical mixer and this optoelectrical detector. And those two devices are two developments that have been done during this project. So in this side, we have the modulator. This modulator has been developed by Aintzane. And this is, I was paying very much attention of the different modulators that Jose Camani was mentioning in this morning. I think he skipped this one. He mentioned lithium niobate, but I think he skipped the gallium arsenide much standard modulators. And in this case, they aim to get higher than 50 gigahertz bandwidth of the modulator. And basically they are choosing it because it's, well, they can reach higher or faster responses They are compliant with the environmental conditions, and they are radiation. They are supposed to be radiation hardened, so they should not fail on the radiation test. They provide more compact footprint than lithium niobate. So then, of course, reducing size and weight is pretty much important. And also they are much more stable than lithium niobate, so they have a bias stability. On the other hand, for the detection side, Alvis, our partner Alvis, has been developing also a 40 GHz bandwidth indium phosphide photo detector module, which is has a very good responsivity, very high bandwidth, but especially it's very low in weight and size. So it's one of the main parameters we see now, which is the size of the devices. So this is a modulator, okay, the optical modulator, and this is a tiny. So the biggest part is basically the coaxial interface of the photo detector. So these two devices have been developed through these last 2-3 years. So the project started in 2020. And this year we have been able to get these samples for reliability testing. And of course, we need to first test their performance and then see if they deviate from the original performance after submitting them to really hard environmental conditions. So after each test, we need to develop this or to perform this testing. So just as an indicative, which parameters we have monitored for the match sender modulator, we have been monitoring insertion losses versus the control voltage. This has been done also not only at room temperature, so in laboratory conditions, but also at low and high temperature operating temperatures. So you can see also the temperature sensitivity of the device. And from those curves, we have also extracted the BPI and the CTF ratio parameters. And for the photodiode models, we have monitored the dark current, the responsivity, and optical and electrical return losses. So they are pretty much, here you can see the characterization also under temperature conditions. You can see they are pretty stable. Only dark current is a bit higher at higher temperatures, which is, of course, obvious. This makes total sense, but it's still quite low, and in fact, it's under their specification, which limits, I think, 10 nanoamps or so. So pretty much the same. So what we have done, once we have characterized those devices, we will test them under those stress conditions that I mentioned before. So mechanical stress, thermal stress, endurance, and radiation. So we will start with mechanical stress. Basically, during the launch, there is a lot of mechanical stress put into anything on board of the satellite. So now taking you have seen for sure the launch of Artemis somewhere in the news, I'm sure. So the spacecraft itself is this one. So it's much tinier than the actual rocket. The rest of the rocket is basically to put it into orbit. And during the launch, these rockets, needs to be detached. So of course, during the launch, the spacecraft suffers huge vibration levels and also mechanical shocks during the detachment of these rockets, which is basically done by pyrotechnic detachment. So they explode. They put pyrotechnics into there to detach them from the main craft. So you can imagine that they suffer really a huge mechanical stress. So we simulate that. We simulate, not simulate by simulation tools, but we simulate the stress levels into a laboratory. Okay, so we perform shock tests. So we fix our devices. You can see the modulator and the photodiode detector here into a test bench, and we subject it to shock. So we shock into the fixture, and we transmit this to the device. And we perform this test in different axes, just in case there is a specific axis that could be maybe more sensitive to these shock levels. And in this case, we have performed this in different axes, and we observe no deviation in performance. So devices after the shock test were performing as before. So perfect, we can prove that they are quite resistant in mechanical sense, but it's not complete mechanical stress anti-vibration is done. So for vibration, we basically apply vibrations of different frequencies and different levels. We typically do a sweep of these vibration levels. And again, we need a fixture and a machine that is basically, it's a shaker that shakes the device up and down according to the given frequency and levels. So again, both devices demonstrated that they could perform well after the vibration, and that they could be at least safe after the launch. Another stress was the temperature stress or the thermal stress. So in this case, one factor on board of a spacecraft is that it's submitted to extreme temperature changes, basically. So depending on if it's under the sun or at the shade side, there can be huge temperature excursions between day and night, basically. So they can they basically suffer these thermal changes. Depending on where the device is placed within the satellite, even they need to be submitted not only to temperature changes, but temperature changes under vacuum. So this is an example. For example, antennas are always placed outside the spacecraft, and hence they are operating under vacuum. So antennas are tested under vacuum and thermal cycles to see if the materials of the antenna are degraded or not. In this case, these devices are aimed to be placed into the satellite into a closed enclosure, so that they don't need to be tested under vacuum conditions, but they still need to be thermal cycled. So we placed the devices into a chamber. Basically, it's a thermal chamber that we can program to do the cycling and monitor the devices. And in this case, they also provided very good results because there was no deviation on the performance of the devices after the test. Another very important point is endurance. As I said, the satellites needs to be reliable for a period of time. So the mission will last for a few years. So typically LEO satellites are meant to live around 1 to 3 years, but GEO satellites are much more expensive and they are not launched so often. So their typical lifetime is around 10 years. So devices needs to be operating during these 10 years. So this is something that we need also to prove. And that any component within the satellite will stay operating during the whole mission time. And this I find also very fascinating, the example of the Voyager. I'm sure that you have also heard about it. It's the NASA's longest mission. In fact, this is not true already because this was done in 2018. It was launched in 1977, and Voyager has been in operation for 45 years, and it's still in operation. So in this case, everything on board of the satellites is still operating after so many years. So it's really impressive. How do we do that? So basically, we need to test the device and test under typical application conditions, so they are representative to the conditions that they will be operating in the space. But of course, we cannot be testing the devices for years. So how we accelerate the lifetime basically by increasing the operating temperature of the devices. If you apply more thermal stress, you can accelerate their lifetime and simulate a whole lifetime of 10 years, maybe 2,000 hours, 1,000 hours. So this is what we did, and we placed both devices in environmental chambers for 1,000 hours in this case. We would like to put it a little bit longer, but due to schedule, basically, we couldn't put it at 2,000 hours, which is more typical for space applications. And then we make them operating to the nominal conditions, basically. So they were biased at quadrature point, and with optical input power, RF signals in there. And for the photodiode photodetector, we also bias them and put some optical inputs at the nominal power levels, basically to simulate the nominal operations that could be representative of the satellite system. And in this case, the results were pretty good, but we observe, in the case of the modulator, we observe a slightly higher insertion losses in there. It's not something weird also because the device is wearing out. Let's say you are operating in and the performance of devices usually degrades. So we need also to check if this degradation is within the specification yet or not. So in this case, it was slightly higher, but it still was acceptable for PARNAT. And in the case of the photodetector model, we observed some dark current instability in the detector, but we have been discussing this with Alvis, with the manufacturer, and basically they suspect that it's not a problem of the photodetector, the chip itself, but something, some passive device within the model. So this needs, of course, some investigation. These failures or changes, or it's not even a failure because the device is still operative and there are specifications, but these deviations from nominal operation needs to be investigated, of course, to find the root cause and to solve it if necessary. Okay, last but not least, because this is pretty specific of a space sector, is radiation. So also we are familiar with these solar storms and these, I'm pretty sure that you have heard that satellites will be off because the solar storm is too high and they will be putting off and things like that. But basically we are in the Earth, we are very protected to radiation, but in space, there are many sources of radiation, many high energy particles going there that are producing radioactive effects, let's say. So this also needs to be tested. We can distinguish different testings, and some of them are more focused on some types of different technologies, basically. So for example, heavy ion testing is done mainly for the digital systems. If they simulate the impact of high energy particles within the silicon chips or any other material chips that can create events, basically. And this is something that we will not be present. We will not be experiencing in microwave photonics, but it's something very specific for more complex systems like memories, for example, so that a bit can change from 0 to 1 or vice versa because of the radiation effect. The two tests that we have done in this case are gamma testing and proton testing. So we have different facilities for that. I put here the picture of our facility in Seville, but you have also really close to here another facility that we have. We also work in there sometimes, and they are basically cobalt-60 radiation sources. So it's cobalt-60 is a radiative element that creates gamma rays with very high energy rays that affect the performance of the devices. And the last testing is the proton testing. So it's basically putting protons into the device, and they can create what is called displacement damage, which is basically a change in the crystalline structure of the devices that can change the performance of it. And for that, we need to move to other facilities. This is one example, which is in Belgium, the UCL, the Catholic University of Leuven. So we have also performed this test on these devices. So we tested the match sender modulator here in Fiamat, which is close to this building right now. And we find basically that the device showed much higher insertion losses after radiation. So this is a performance, the highest curves at different steps. This test is done at different cumulative doses. So you irradiate the device, and after some time you take the sample out, you measure it, and then you place it together. So you accumulate the radiation dose until you reach the target level. In this case, it was 100 kilorats. And at the final stage, we found that these insertion losses were much higher and the device was not as good anymore. After the radiation, there is another process that needs to be done, which is the annealing. This process is basically that some devices or some technologies can recover for their radiation effects if you give them some time, let's say, and it can be further accelerated if you place them at high temperature. So the annealing process is done in 2 steps. One is done at room temperature, and afterwards it's done at high temperature. And in this case, even after the annealing process, we still kept a very high insertion losses. And there's another funny thing we observe. Well, it's funny. It's that the fiber ferrule was changing the color. So one of the things that we are analyzing now is if this can be the root cause of the insertion losses that we are finding in the model. So we need to investigate further where the deviation is coming from, but this could be one of the reasons. So the connector performance is not as good as before the exposure. The material has been affected by the radiation effects, and hence we are not getting the same performance out of the model itself. Even with annealing, we observed that the color was somehow recovering, but it was not fully recovered in the original state. On the photodiode detector, we did this radiation test directly on chip. So we used this chip on carrier. Okay, so we place the photodetector onto a carrier with these signal ground paths to measure the device directly. So in this case, we needed to change the parameters to monitor, and we could measure basically dark current and the electrical return losses of the photodiode, but not all the parameters that we were measuring at model level. We did this test in the Rad Lab facility, the picture I showed you before, in Seville, and we placed these chip on carriers in a bigger carrier. This is 5 centimeters by 5 centimeters, so you can see how tiny the photodiode is. And we then placed this into a box that it's exposed under the cobalt source and in the facilities. And in this case, we observed no sensitivity at all. So devices were performing the same as in each step of the radiation, and also after the annealing, so everything went fine. So it was pretty fine. And I told also about proton testing. So for that we traveled to Belgium. Not myself actually, but anyway, this is the facility. So it's the radiator is over here, and here you put the sample. So this is basically the same platform like here. And this we put our photodetectors. So they are really tiny in there, but they are getting all the radiation effects. And we tested at different radiation dose levels. And in this case, we observed that some of the devices were showing slight sensitivity at the highest radiation levels. So you can see the blue line is the dark current of the photodiode before the radiation, and after the radiation we got slightly higher dark current. Sorry, it's a really small deviation because in fact the specification of the device is 10 nanoamps for dark current, and we were even below 1 nanoamp. So we can still say that they are radiation harmed devices. And in the electrical performance, in the electrical return loss, we observe no further changes. So regarding the match sender modulator, we did also the test, but due to scheduled reasons, the samples were sent directly from Aintzane to the facility and back again to Aintzane, so I cannot show you any results, but they also performed well. And finally, after doing all this reliability testing, the final step is typically a destructive physical analysis. So basically you take the samples, or few samples, not all of them. Typically you use 2 or 3 samples, and you basically need to inspect the physical construction of the devices after all the stresses. just to see if there is any crack, for example, produced by thermal stress or for mechanical stress, and observe the construction itself. So for that, we employ many different techniques that are applied in order to basically we are digging into the device. So we are analyzing the whole assembly by radiographic inspection. Then we open it and perform a visual inspection of the inside, and then go step by step analyzing the bondings, analyzing the chips by scanning electron microscopy, and testing the bonds by pulling them. We do also fiber proof tests. So it's a bunch of tests that completes the analysis of the devices. And this is currently, it's currently ongoing. So these images are not actually from the devices. They are just examples of test results from other type of devices. In fact, I would say this is an image, but it's just to show you a bit an example of how a destructive physical analysis looks like and what's the aim, the final aim. So this will complete basically the reliability testing performed within the framework of the project. And I would say that we have been able to, well, not us, but our colleagues, our partners have been able to develop a space-grade match center modulators and photo detectors. We have performed the reliability testing at module level with successful results. And finally, there is also another activity ongoing by in this case, it's Thales who is taking care of that. They are building system level demonstrators, covering the proposed system in here to verify the solution, the complete solution, to verify that those devices are performing as expected and they are able to perform at system level too, and they will also perform environmental testing at system level. So they will submit it to mechanical test and thermal test, I think. So I would say yes, those are the first steps for those devices to go into a satellite. But of course, there are many more to come. And I would say these are also the first steps of microwave space photonics. And there will be many more also to come. So future is challenging us to develop new things and to put them into space for our applications, basically. So thank you very much for listening. And yeah.